Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. Today I am giving the lecture on Chemical Engineering Thermodynamics 1. This is my lecture 6. So in today's lecture we will discuss about the enthalpy. In the previous lectures we have discussed about the enthalpy, constant volume and constant pressure, what will be the equation of the internal energy, and what are the examples related to this enthalpy and this at constant volume and constant pressure the energy equation can relates, and the heat capacity we have discussed. So we got the get the new terms which is called the specific um, heat capacity, so which is CV at constant volume. So it will be related to the rate of change in this when the changes in the internal energy with respect to the time temperature. So this is the del U upon del T, which is at constant volume, and you will when it will be on a constant pressure, so it will be Cp equal to del H upon del T. So after the reducing that equations, we will getting this the specific heat, which is at constant pressure and constant volume. So these things we have read in the previous lecture. So in today's lecture we will discuss about the first law of thermodynamics for flow process. In flow process, what are the things required to solve the system, and in the previous ones we have defined the heat capacity, and we will give some examples of the heat capacity, how we can calculate the heat capacity, or how this heat capacity can be relates to the different at constant volume and constant pressure. So we will do some examples related to this, and then the mass energy balance for open system. So we will write the equation for the mass when you will do the mass balance for open system and the energy balance for the open system. So these two equations we will define. We will and what are the different examples related to this balances for the mass balance or energy balance. We will do some examples of it. So this is today lecture we will discuss in this lecture 6. Okay, so now we will start our lecture. So so we have already told you that the heat capacity example we will discuss first. So in heat, so this is the first example. So when air at 1 bar and 298.15 Kelvin is compressed to 3 bar and 298.15 Kelvin by two different closed system, mechanically reversible process. So the first things that the cooling at constant pressure followed by heating at constant volume, and the second B the condition is the heating at constant volume followed by cooling at constant pressure. So now you have to calculate the heat and work requirement and the internal energy, change in internal energy and change in enthalpy of the air for the each path. The following heat capacities for air may be assumed independent of temperature. So we have to calculate these things for the system for the two different paths, and this specific heat for constant volume, which is 20.785 joule mole inverse K inverse, and this and at constant pressure it is 29.1. So this is already given, and the assumptions are for assume also that the air remains a gas for which PV upon T is a constant. Okay, and the regardless of the changes it undergoes at 298.15 and 1 bar, the molar volume air is 0.02479 meter cube dot mole inverse. So this is our example. So now we will do the solution of this example. So how you will solve? In each cases, take the system as a 1 mole of air contained in a imaginary piston or a cylindrical arrangements. Okay, that cylindrical arrangement we have already seen in the previous lectures. So because the processes are mechanically reversible, so the piston is imagined to move in the cylinder without friction. So now we will calculate what will be the final volume of the system. And if you will see, this is you see this is a path when at constant pressure and the volume. This is a graph which is at constant pressure and volume, and this is the graph between the pressure and the temperature. Okay, so in these two graphs the different paths are showing. This is when you will see in the pressure and volume path. So you are seeing the initial state is here, and this is the final state. There is a two path. The first path is this one, they can follow this one, and the second path is this one, they can follow this part. So you will see when initial volume, if they will follow this path, at this point the pressure is constant, and the volume is changing. Okay, when the pressure is constant and volume is changing, so this is path is following, and then it is a path A, and then it will be, and now the constant pressure is changing and the volume is constant. So this is the first condition. Okay, so this is the A path, and now if you will see this path initial state, so when you will follow this path, at this point the volume is constant at heating stage, and followed by the cooling is happening. Now the pressure is constant in this point. At the 3 bar the pressure is 3 bar, and then it is constant. So these are the two paths which is showing in this graph, which is the graph is between the pressure and the volume. And if you will see this one in the second graph, this graph between the pressure and the temperature, and you will see this is the initial state and this is the final state. Initially when you will follow this path, so in this path initially the you are seeing the pressure is constant. Okay, and the pressure is constant, and then it is going the temperature is also changing and pressure is also changing, and the constant is I think volume will be constant. And if you will follow this path, so here also the temperature and pressure both are changing, and but when you will follow this point here to here, so it will this is showing the pressure is constant. So this is the another path which is following the thing. So now we will solve this system. So when you will calculate the volume, so initially you are seeing the final volume be V1 initial volume they have given. You can see here it is assume molar volume of the system is 0.2479. it is already given, and the P1 and P2 is there because it is changing from 1 to 3 pressure. So it is already given. The P1 is 1 and P3 is P2 is 3. So you will get the final volume which is 0.008263. So P1 V1 equal to P2 V2. So this is a simple formula, so you can easily calculate. So if you will during the first part of this path, as you see in the figure 1, so air is cooled at the constant pressure at 1 bar until the final volume of 0.008263 meter cube is reached. Okay, so the temperature of the air at the end of this cooling step is so T equal to when you will calculate which is, if you will see, T1 V2 equal to V1 T2. So that means that T directly T inversely proportional to the volume. So this is the formula, and we know the initial temperature is 298.15 and the final volume is 0.08263 and 0.02479 is the initial volume. When you will put these values inside into this equation, so you will get it 99.38 Kelvin, which is the final temperature of the system. So thus for the first step you have seen this thing. So now we will calculate the how much energy heat is required for the system. So we know the Q equal to del H, and this del H means the enthalpy, change in the enthalpy, and we have already discussed that formula in the heat capacity. So at constant pressure, so the enthalpy will be Cp delta T. Then you will calculate this. So what will get Cp, you know that 29.1 it is given, and the final temperature is 99. This is already calculated, and an initial temperature is 298.15. so you will get it minus 5784 joule. This will be the heat you will produce during the system. Now you will calculate the work. So work is minus P dV. So initially pressure, you know, 10 to the power 5 1 bar. So when you will convert into the atmosphere to the Newton meter square, so then Pascal or in Pascal, so you will get it 10 to the power, you have to multiply 10 to the power 5. So and the volume, initial volume, you know, which is 0.08263 minus initial volume, this is 0.02479, then you will get it the work, which is 1653 joule. So now you will get this heat and work for the system, and then you will calculate the internal energy for the system. So how you will calculate? So this is already we have discussed in the first law of thermodynamics, the internal energy. So del U equal to del H minus del PV. So then the pressure is constant for the system, so then del H minus P dV. So del H enthalpy you have already calculated, which is minus 5784, and P dV, which is the work done. So if you will which is already calculated, so 1653, which is this work, and then you will combine it, so you will get it the final answer. So this is minus 4131 joule. This is the internal energy produced during is stored in the system. So next, the second step is at constant volume V2 with heating to the final state. So in this system, so when the work is 0, and for this step, so the internal energy del U, which is equal to the Q, and if you will calculate, which is Cv delta T. So the this specific heat at constant volume, which is 20.785, and the temperature change is for 298.15 to 99.38. so then you will get it the internal energy, which is 4131 joule for this step. And if you will calculate the work done VdP, so so volume you know 0.08263 meter cube, and into the pressure changes from 1 to 3 to 1, or so it is you will get it the 2. The changes in pressure is only the 2 bar. So when you will change this 2 bar into the in the Pascal SI unit, which is in Pascal, so it is 2 into 10 to the power 5. You have to multiply this, so you will get it 1653 joule. which is a work done you will produce. So now you will calculate the enthalpy of the system. So what will be the enthalpy for the system, and we know that the enthalpy is del U plus VdP. Okay, so then this equation we have already derived in the previous lecture. So you will see this internal energy is 4131 and work done is VdP, this is 1653, and then you will get it the 5784 joule. This is the change in enthalpy in this step. So for overall process, when you will see how much the heat is produced or released during the system during the following that path, so that will be the Q will be the minus 5784 plus 4131. The enthalpy is already given, and this internal energy which is already given. So if you will sum of these things, so you will get minus 1653. This will be the energy released. So now if you the total work done will be the initially it is 0, so because there is an volume is constant, so that is 0. When it is changing, so 1653 plus 0, then you will get it 1653. That will be the total work done which is done by the system. So now if you will calculate the internal energy total for the system, so that will be the del U equal to minus 4131 plus 4131 in the previous path and this path. When you will sum of this thing, so you will get it the 0. There is no change in internal energy. So the enthalpy, if you will see the both the initial path and the first step and the second step, if you will sum of this how much the change in the enthalpy, so that then you will sum up. So minus 5784 plus 5784, that will be the both are same, so it will be the 0. Another, there is a no change in the enthalpy is also during that system. So the notice that the first law del U equal to Q plus W, so it will be proved that applied to the all process is satisfied. Okay. So the property change internal energy and enthalpy calculated for the given change in state are the same for both paths. On other hand, the answer of part A and B shows that the heat Q and W depends on the path. So this is the things now we will understand during this example. So in the B path, so for the two different steps of this path produce the same final state of the air. So in the first step, air is heated at constant volume equals to the V1 until the final pressure of 3 bar is reached. So the air temperature at the end of the step is, so because that part the constant volume, the step is W equal to 0. The constant, because work done is Vp dV. So the dV, there is no change in volume, so the work done will be 0. So when you will calculate the heat, so the Q equal to del U, it will be directly, because we know that the del U equal to Q minus del W, so that W will be 0, so it will be related to the internal energy, which is CV delta T. The CV we know that which is 20.785, and the change in temperature is 894.45 minus 298.15, and so you will get it 12394 joule. That will be the heat produced during the system, and the VdP equal to 0.02479. It is already given the volume, and the pressure is, there is a change in the pressure is 2 bar, which is 2 into 10 to the power 5 when you will change into the Pascal. So then you will get it this 4958, this will be the change, and the enthalpy when you will calculate, so del H equal to del U plus V del P. So then you will combine put these two values, the internal energy and this VdP value. So then you will get it the 17352 joule, that change in enthalpy during the system. In the second step, air is cooled at P equal to 3 bar to its final state. So then you will calculate the heat Q, which is equal to and change in enthalpy, and because it is at constant pressure, so Cp delta T. So if you will see in this equation, if you will see the constant pressure, so it will directly equal to this one, so which is 29.1 specific heat, and the change in temperature is 298.15 to 894.45, as graph shown. So then you will get it, the change in enthalpy will be minus 17352 joule. So that will be the change in enthalpy, and the work done will be the minus P dV at constant the change in the volume. So the pressure is final state pressure will be the 3 into 10 to the power 5, and 0.008263 is the final volume, and initial volume 0.02479. So then when you will put these values, so you will get it the 4958 joule, that will be the work is done by the system. So and then you will combine these things, and you will get the internal energy, that del U equal to del H minus del PV. So because it is the constant pressure, so del H enthalpy will be the minus 17352, which is previously calculated. Here you have already calculated, and the change in the P work done is this P minus P dV, so which is already calculated 4958. So then you will combine both of the energies, so you will get minus 12394 joule. This will be the change in the internal energy during the system. So for the two step combined, the heat will be the Q equal to 12394, this one, and in the second step it is minus 17352 joule. Then when you will combine it, so it is minus 4958 joule, and the work done, so that will be the W equal to 0 plus 4952, so then it will be the 4958. And the internal energy, so initially in the first path and the second path both have the same internal energy, then you will combine it, so it will be the 0, there is no change in the internal energy. So and the same thing for the enthalpy, so the del H 17352 for first path, and the second path minus 17352. So and then you will combine it, so there is no change in the enthalpy. So we have seen on the both path the internal energy and enthalpy are the same for the both path, and it is dependent upon the heat and work for the for the A system and the B system. In the both cases, it is dependent upon heat and work done. So now we will discuss about the second example for this system. So now you will calculate the internal energy and enthalpy changes resulting if air changes from initial state of 5 degrees centigrade and 10 bar. So where its molar volume is 2.312 into 10 to the power 3 meter cube mole inverse, and to a final state of 60 degrees centigrade and 1 bar. So the assumption for this system is the air remain a gas for which PV upon T is constant, and the specific heat at constant volume is 20.785, and heat is at constant pressure it is 29.100 joule mole inverse K inverse. So this is the second example. For the solution, when you will solve this system, so because the property change are independent of the process, The calculation may based on the any process that accomplishes the changes. Here we have choose the two-step mechanically reversible process wherein 1 mole of air is the first A cooled at constant volume to the final pressure, and the B is heated at constant pressure to the final temperature. Of course, other path could be chosen and would yield the same results. So because when you will change into the in Kelvin, because it is 5 degrees centigrade, so it when you will combine with the this 273.15, so it will be the 278.15, that will be the when you will change degrees centigrade to the Kelvin, so you have to add it the 273.15, and the final temperature it is given the 60 degree C, so which is 333.15 Kelvin, you will get it. And when so you know about this PVT equal to KT, the ratio the temperature and pressure which constant for the step 1. So in the intermediate temperature between the two step is so T dash will be so the change in the pressure is 1 bar and 10 bar. This is the change in the pressure, and so you will get it the another temperature which is 27. Intermediate temperature will be at 10 bar, it will be 27.82. so the temperature change of the two steps are del T equal to 27.82 minus 278.15. So the change in temperature will be the minus 250.33 Kelvin. And for the B path, so this 333.15 minus 27.82, so the change in temperature will be 305.33 Kelvin. So this is the change in the path B. So the for the step 1 A, so the internal energy del U A which is equal to del CV del T A, so because it is a constant volume, so specific heat you will get 20.785, it is already given, and the change in delta TA which is minus 250.33. so the change in internal energy you will get it minus 5203.1 joule, and change in enthalpy which is equal to the del UA plus VDP, that is already drive in the previous lectures. So then you will put it all the values of this internal energy and change in the pressure. So you will get the internal energy minus 5203.1 joule and 2.312 which is volume into 10 to the power 3, and the change in pressure is because the 1 bar to 10 bar, so the change is changes in the 9 into 10 to the power 5 Pascal. So then you will get it minus 7283.9. This is the enthalpy change during the system in the step A. Now you will in the step B, when the final volume of the air, then you will calculate the V2 equal to V1 P1 T2 P2 V1 T1, sorry. So the enthalpy you can easily calculate the this when you will put the pressure and the temperature and the volume, so you can get the final volume of the system. So that final volume will be and you can easily calculate because all the things are given. So now you calculate the change in the enthalpy for the CP at constant pressure delta TB. So change is 305.33 and 29.10, it is a specific heat. So your enthalpy change is 8885.1 joule, and when you will calculate the internal energy del U equal to del H minus P dVB. So in enthalpy you know, and the change in volume V1 you know that, and V2 already you have calculated. So the final calculation the V2 will be the 0.0279, and the initial volume is already given 0.0231. So the change in volume will be, you can easily get, and this is your change in enthalpy. So when you will combine both, so you will get it 6347.1 joule. That will be the change in internal energy for the system. And for the two step together, when you will combine the two step, so the change in internal energy will be minus 5203.1 plus 6347.1. so then you will get 1144. So you can see here, this is the initial one, and this is the where this is the final one in the path A and path B. So this is 1144, it is the change in internal energy. So and the change in enthalpy will be minus 7283.9. So here for the path A, and path B it is 8885.1. so you will get the change in enthalpy 1601.2 joule. So we have seen how much the change in internal energy and change in the enthalpy during that two paths. Okay. So in the previous cases we have discussed about the examples of the heat capacities. Now we will for the open system we will do the some mass and energy balance, and we will derive the equation for the mass balance and for the open system. Okay, although the focus of the preceding sections has been the closed system, so all the systems are closed, and there is a cylinder and there is a piston, and piston inside the cylinder there is change in the volume and pressure, because and it is closed by the piston. So that will be the closed system. Now we will discuss the concept presented fine for more extensive applications. The law of mass and energy conservation applies to all processes that can open for the closed system. Indeed, the open system includes the closed system as special cases. The development of equation in the wide practical applications. So this open system have very wide applications, practical application during our daily life. And so initially we have to measure the flow. The open system are characterized by the flowing streams. There are four common measures of flow. So the each one are the mass flow rate, which is m dot rate. We generally the dot is a representation of rate. So you can also write del m upon del t. So the rate is which is changing with respect to the time. Okay. So this dot is a symbol for del by del t, the change in the mass. And the molar flow rate you will define by the n. And so the rate is molar flow rate is n dot, and the volumetric flow rate is q, and the velocity is u. So the measure of flow are interrelated. So the m dot equal to the molecular weight into this molar rate, which is n dot, and this volumetric flow rate equal to u into a, where a is area and u is the velocity of the fluid. So the which is defined this like the capital M is the molar mass, and the A is cross sectional area for flow. For importantly, the mass and the molar flow rate relates to the velocities. Okay. So this mass which is equal to u a rho 1a, this is the first equation, and this molar flow rate, which is u a rho. Okay. So the area for flow A is cross sectional area of the conduct, and rho is the specific or molar density. Okay. although velocity is a vector quantity, its scalar magnitude u is used here as the average speed of a stream in a direction normal to A. Okay. So the flow rate m dot and n day, mass flow rate or the molar flow rate represent and the volumetric flow rate represent the quantity per unit of the time. So the velocity u is quite different in nature. So as it does not suggest the magnitude of the flow. So it is important for the design parameters. So these are the very important for the design parameters, all the flow rates. So now we will discuss about some examples of how we can use these flow rates for the different system, for the open system. In a major human artery with an internal diameter is 5 millimeter and the flow of blood average over the cardiac cycle is 5 centimeter cube second inverse. So the artery bifraction, when you will split into the two identical blood vessels, there are each 3 millimeter in diameter. So what are the average velocity and the mass flow rate upstream and the downstream of the bifraction, and the density of the blood is 1.06 gram per centimeter cube. So now we'll do the solution for the system. So the average velocity is given by the volumetric rate divided by the area flow rate, area flow. So thus the upstream of the bifraction where the vessel diameter is 0.5, when you will convert it in the centimeters, it is 0.5 centimeter, and we know that the volumetric flow rate is q equal to area into the velocity. So you know about the you can calculate the area, which is pi by 4 d square. So it will be the diameter is 0.5 5 into 0.5 centimeter. So then, and the q it is already given, which is 5 centimeter cube second inverse. So you will get it the velocity, which is 25.5 centimeter second inverse, and the downstream of the bifraction. So the volumetric flow rate in the each vessel is 2.5 centimeter cube second inverse, and the vessel diameter is 0.3 centimeter, and the mass flow rate in the upstream vessel is given by the volumetric rate times the density. So you will see the rate of change in mass up is 5 centimeter cube dot second inverse. So this so you know the what is the rate of change of mass flow rate, which is density is 1.06. So it will be 5.3 gram second inverse. And similarly for each downstream vessel, so the m down for this 2.5 centimeter cube dot second inverse, and the density 1.06. So it is 2.65 gram second inverse, which is of course the half the upstream value. For up it is the 5 and it is the down is the 2.6, which is generally half. It is half. So this is the our second example. Okay. So in the today lecture we have discussed about the examples and the mass balance for open system. Mass balance for open system. We have not discussed about the energy balance. This energy balance we have not discussed today. Okay, we have discussed only the mass balance. So these equation we have not discussed, only the continuity equation we have discussed here today. For the next lecture, we will discuss about the energy equation for the system, and the energy balance for the steady state flow process, and the general equation, and the flow calorimetry of for enthalpy measurement, and the examples of it. So that thing we will discuss in the next lecture. So thank you very much for listening this lecture 6, which is given the brief examples of heat capacities for the closed system, and the open system we have also discussed today, for the how you can calculate the rate of change of mass or the volumetric flow rates. Okay, so these things we have discussed. If you have any doubt related to this lecture, so you can email me, and this is my email address, chemicalsaniraj@gmail.com, and this is my website. You can also see, if you have any other things, you can also read here. This is my website. So thank you very much for listening my lecture.